Hello! Very special day, because I'm going to give you the solution to a very difficult problem, the most difficult one that I have posted so far. So on a special day I decided to wear a special hat. This is my Mondrian hat. These are my Mondrian glasses. Of course they haven't been designed by Mondrian in person, but they are the immediate result of the style movement of the 1920s, of which P. Mondrian was the godfather. So let's talk about the problem. We have a rod. The rod has a certain radius, and the radius is much smaller than the length of the rod. In my case, the radius is about 1% of the length. We make the assumption that the mass density is everywhere the same in the rod. And also we have to assume that the radius of the rod here is the same as here, is the same as there. So quite a few assumptions we have to make to solve the problem in an easy way. Remember our problem of 2 weeks ago? We oscillate the rod from one end, and the question was, what is the period which we called capital T? You have seen the solutions already. The period capital T is 2 pi times the square root of 2L over 3G. All right. The question then was, for this week, is there any other point about which I could rotate the rod which would have the same period of oscillation as the one when we rotate from the end? So, for instance, would there be a point here, I call that point P, for which capital T is the same as it was when we rotated from here? Before we address the mass, which may be a little complicated, if we chose the point P, the point about which we rotate, if we chose that to be at the center of mass, which is very close, of course, to the exact middle of the rod, then the period of oscillation would have to be infinitely large, because the torque in this direction would exactly cancel out the torque in that direction. So there is no preferred equilibrium position, so it will not rotate at all. If we let it go, it will not oscillate. I try to drill a hole there as accurately as I can in the middle. It's not so easy, believe me. Okay, now I'll change the position. And it doesn't go to an equilibrium position. Alright, that's what you expect. You expect the period to be infinitely large. Therefore, it would be entirely reasonable if you expected that there is not any other point, P, for which the period would be the same as this period. And the reason why I say that is that if the period when we rotate about the center of mass is infinitely large, it is quite possible that for any distance from the end, we call that distance x, remember, that for any distance x different from 0, the period would only get longer and longer and longer and longer and longer, and ultimately infinitely high when we rotate about the center of mass. Not an unreasonable expectation, but surprisingly, that expectation is wrong. So let's now go over the math, which is not so simple. I have to use the camera and hold it in front of my equations, so my hands are not very, very stable. Your hands wouldn't be either. So there will be a little bit of movement. I can't help that, with my apologies, but it's the best I can do under the circumstances. So you see here a drawing that you have seen before. You see the rod here. We offset the rod over an angle B. We rotate the rod about point P. The rod has length L, mass M, and the gravitational acceleration is G. We call the distance from P to the end x. And x can obviously be expressed in terms of capital L. So you can make x 1/4 of L or 1/5 of L. If you choose P to be at the center of mass, then x would be 1/2 L, of course. So now we go to the heart of the physics. And this is explained in great detail in my lecture 21 of 801. And of course it was also discussed during the solutions of my first problem, where I asked you the period of oscillations about the endpoint. The moment of inertia about point P multiplied by the angular acceleration, which is the second derivative of the angle, plus the torque about point P must be 0. And since we call the angle B, the second derivative would then be B double dot, which means the second derivative in time of that angle B. And if now we only look at small angles, then the oscillations are a simple harmonic oscillation. Sine B, the sine of the angle B, if that is approximately equal to B, and that's only true for small angles, then we get this simple harmonic oscillation. We call that the small angle approximation. So let's first evaluate what I of P is. Look at the rod again. You see point P. It's at a location x from the end. And we now have to find the moment of inertia about point P. And I make use of the parallel axis theorem. The parallel axis theorem says that the moment of inertia about point P is the moment of inertia of rotation about the center of mass, I call that I of C, plus the mass times d squared, if d is the distance between the center of mass and point P. You can all find in tables what the moment of inertia is for rotation about the center of mass. That is 1/12 ml squared. So the moment of inertia of point P is then 1/12 ml squared plus md squared. But d is L over 2 minus x, because from C to the end of the rod, that is L over 2. And from the end of the rod to P is x. So therefore d is L over 2 minus x. And if you want to get the final answer for the moment of inertia about point P, which I need later on, then you have to substitute for d in this equation L over 2 minus x. And I will do that, and you will see then the result of I of P. But you should be able to do that on your own as well, of course. So now we have I of P as a function of x. Now comes the hardest part. The hardest part is to calculate the torque about point P. Well, there is a clockwise torque, which is the result of the rod on the right side of P, and there is a counterclockwise torque, which is the result of the piece of rod on the left side of P. The rod on the right side of P has a mass which is m times L minus x divided by L. The mass of the entire rod, length L, that mass would be capital M. But the rod on the right side of P is not length L, is only length L minus x. So therefore the mass is m times L minus x divided by L. And so the gravitational force acting at the middle of that piece of rod, that gravitational force down is mg times L minus x divided by L. So now we have to do the cross product because we need the torque. And the torque is the position vector cross product with the force. So this is the position vector from P to the force, and the length is L minus x over 2, that is rather obvious, and this is the force. You take the cross product, that means you also need the sine of the angle B. But for small angles, you can change that sign simply by a B. If you now go to the part on the left side of P, that's a counter clockwise torque. The mass of that piece is mx over L. And so the gravitational force down, which starts at the middle here, is mgx over L. mgx over L. And the angle is B, and the position vector, this is the position vector, that position vector is obviously x over 2. Because from here to here is x, so this is x over 2. So now you have the sum of two torques. The clockwise one has a positive sign, and the counterclockwise one has a negative sign. And if you do that, and you add them up, you will find this value. And the sign of B, as you see, has been replaced by B, because we only look at small angular approximations. So now we're going to use the result for I of P, and for tau of P, and we put that in the equation that you see right here. So I of P, you see between brackets there, times B double dot. I already discussed with you how you calculate I of P, and if you did that on your own, you should find the value that you see here. So times B double dot, and then here you have the torque that we just discussed, and the sum of the two must be 0. Now, when I reach this point in my calculation, this point, I did a check that every physicist would do. I substituted in that equation x equals 0 to make sure that I find that the period is 2 pi times the square root of 2L over 3g. But x equals 0 means that we oscillate the rod from one end. And indeed, that's what I find. I did a second check. I put in x equals 1/2 L. And look, if you put in here 1/2 L, the downstairs is 0. And so indeed, the period goes to infinity. So I felt more than encouraged that that result is correct. So now we go back to our question. is there a value for x for which this t is the same as this t? So you put them equal to each other. You get rid of your 2 pi, of course. You also get rid of the square roots. And lo and behold, you find 2 solutions for x. It shouldn't surprise you that you find x equals 0, but it should surprise you that the other location is L over 3. So when you rotate the rod about a position L over 3 from the end, you get the same period. You get the period 2 pi times the square root of 2L over 3g. Because I went one step further. This is a step that may be too difficult for you. I don't mean to insult you, of course. So I decided to plot this function. I wanted to see how t depends on x. Because I still found it strange that there are really 2 positions with the same period. Because my intuition said, well, the period will probably gradually increase with increasing value of x and goes ultimately to infinity. But that is not true. So when I plot this function, you see the result here. Vertically I plot t. And horizontally I plot x over L. And I plot t in units of t0. t0 is the famous 2 pi times the square root of 2L over 3g. And now you see that if x is larger than 0, that the period goes down. But then gradually it turns up again. And so when x over L is 1/3, then the period here is the same as it is here. So for x equals 0 and for x equals 1/3 L, you have the same period. And then if you make x larger, it goes very quickly to infinity. Now, of course, I was also curious, and maybe some of you can do that, but that's not so easy. I was also curious at what value for x is the period the smallest. And I found, I can't tell you how I did it, but I found that that happens when x is 21% of L. 21%. It's right here. I put a little dot there to remind me. And the period then is about 6.9% lower than t0. So, if I summarize, my rod had a length of 1.055 meters plus or minus 3 millimeters. If I make measurements and I time 10 oscillations, then on the 10 oscillations I have an uncertainty of 2/10 of a second. That means on one oscillation I only have an uncertainty of 0.02 seconds, 2/100 of a second. I made that measurement with my rod and I find 1.69 plus or minus 0.02 seconds. And I showed you on the solution of the first problem 2 weeks ago how I arrive at that number. Then I also calculate the period for x equals L over 3. Not calculate, sorry, I measured it. I drilled a hole there and I measured it. And lo and behold, it is within the uncertainty the same as at x equals 0. And then, of course, I drilled another hole in the rod at about 21% of L from the end. And I find now that in my case the lowest period that I will get then is about 1.56 seconds, plus or minus 200ths of a second. You can confirm that that is about 7% lower than the value at x equals 0. So in order to complete my mission, I wanted to demonstrate to you also by measuring the period when x equals L over 2. And I knew that would take infinitely long. But I am already 81 years old, so I felt a little uneasy about waiting that long. So what I did was, I watched the rod after I put the pin right at the center of mass. I watched the rod for one whole day, that is 86,400 seconds. And I timed that very accurately to an accuracy of 0.02 seconds. And then I decided to give up. I didn't sleep all night. I was up 24 hours. All I can say is that the period is larger than 86,400 seconds. I hope you forgive me for this. If you want to measure it and you want to wait infinitely long, be my guest. Okay? Have a nice day. Yes, 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 we're still friends. And take care.